Hey, hi everyone. Good evening. See, very low attendance today. I'll wait for 2 more minutes. We'll start in 2 minutes. Okay. Yeah, so let's start actually. We'll not waste more time. So, today we'll be looking at a different genre of problems. Okay. We'll not go into naming the genre, so there is no specific name, but it will follow a specific way of solving the problems. Okay. We'll try to solve them in a specific way. Having said that, all the four problems will be completely different. So, yesterday we had two problems, the initial, the parentheses problems, almost similar, which could have been solved with stack, right? Today the problems are all different, but they can be solved in more or less the same way. Okay, and the optimal solutions will involve, like obviously, all the solutions that we look at. So there will be a brute force solution, and the optimal solution will be much simpler, much more elegant, and will be and that is what we'll be looking at. Okay, so let's go into that. Let me share my screen. So let me know once the screen is visible, the audio is clear. Anyone can confirm the screen is visible, right? Okay, cool. So yeah, let's go. So we'll be looking at a very simple problem to start with. Okay, but all the problems try to think of a solution which is better than the brute force today, because the brute force solutions are very simple, and but the problem with them is they have much higher time complexity. So what we will directly look is for optimal solutions. Okay, so let's say we have a sorted array. We have a sorted array with duplicate values. So let's say we have something like this. Okay, so input is a sorted array with duplicate values, and what we need is we want to remove the duplicates and add the remaining elements with zeros. Okay, so what we are looking for is we are looking for something like this. And then something like this. Okay, so this is the input. This is the output, and this has to be done in place. So you will be changing the current array itself. So the problem is, given an input array with given a sorted array with duplicates, given duplicates, so we are trying to find push all unique elements to the left, and pad remaining elements with zeros, right? And pad zeros to the right. So this is our problem one. So let's think of how we can approach this problem. So take 5 minutes time, think about it a bit, how you can come up with a solution. Note that you cannot use any extra space, right? So there is no scope of using extra space. You have to return the current array itself. So how we can maintain, or how we can figure out the how you can move the elements accordingly. Anyone wants to take a dig at the probable solution? So we have a sorted array with duplicate elements, with possibly duplicate elements. It might be that there are no duplicate elements at all. So you already have the answer with you. So if there are duplicates, you have to push all the unique elements to the left, and to the right you have to put zeros, whatever the empty spaces are there. Okay, Rudnan has a solution, possible approach. Anyone else? Give 2 more minutes. Anyone? Anyone else? Anyone new who wants to chip in? Okay, there are no other possible approaches. So Rudnan, you want to explain how you want to solve this problem?
Sir, we could first have 2 pointers at the beginning of the array.
Okay.
As we know, the array is shorted, so we could traverse one pointer, and when we see a element greater than the last maximum we have seen, so we would increment the second pointer to the next one position and make that element equal to that. Then when the first pointer reaches the end, we would have seen all the elements in the array, and the starting, like all the distinct element, and they would have been uh, up to a certain position. Okay, wait. Like
Okay, so let's formalize the approach a bit. So let's have the array. So we have 1, then we have 2, 2. Okay, so we are starting with 2 pointers here, right?
yes,
So what do we do?
the first pointer is going to traverse all the elements.
Okay, so let's call it the first pointer. Let's call this the second pointer. First pointer is going to traverse all the elements. So it starts traversing. Say it goes here.
Now that yes, now that we have seen an element which is maximum than the greater than the previous element, that is
Okay,
the second pointer is pointing, we
right.
would increment the pointer
Okay,
and make this element equal to the first pointer, like the first pointer is pointing to.
yeah. So first pointer to anyway is pointing to this. Yeah, second pointer also moves here, right?
Now, yes,
So which means that this part of the array is now valid. So this part of the array has now, it has unique elements, is guaranteed to have unique elements. Okay,
yes,
then what we do, then we move the first pointer again, because this is anyway moving,
we skip this too, and when we
because
see
if it is equal to the second pointer we skip it, so we move it until we find a new element, until if
yes,
we find an element which is not equal.
greater,
Yeah,
as the array is sorted.
correct. So greater because the array is sorted. So the moment we find something new, we say that the second pointer, we will increment 1 and update this value essentially,
Yes,
right? So we increment this and update this value. So we make this say 3, and this is our second pointer now, right? Continue to increase. We continue to increase the first till we find something different than the second. Now we find something different than the second. Great. So we again move second by 1 place and update this. So this becomes our second, right? Again we move the first pointer. We see something different than the second. So we move second by 1 place and update second. Again we find something different than the second. We move second by 1 place and update the second. Same thing here. We find something different. We move second by 1 place. We update the second and we have moved 1 place. So now this part of the array again is sorted. So wherever second is there, from beginning till second at any point of time is sorted, right? Then we continue to move. We see, okay, it is still equal, nothing else to do. We have reached the end, so we are done. So one pass of the array is done, right? Now what we do? Yeah.
Now we have a second for loop, and in that now we increment the second by 1, and until that second is equal to end, we make them all 0.
We make them all zeros, right? So until the second is, until second reaches the first or second reaches the end, either is fine. So we make everything else as 0. So now this part of the array, the left part, whichever had the initial second, that has the unique elements, all the unique elements, right? And the other elements are all marked as 0, right? So this is a good 2-pointer approach that we can have. Okay, so we start from the beginning, first and second. If we see that first and second are equal, so we don't need to keep first and second on the same place. because we know the first element has to be there, right? So we can move the first pointer one step ahead, and second pointer we can keep there, first place itself in the first index itself, and then do the comparison. Right? So whenever we see that the two numbers are different, or basically first is greater than the second, we move the second pointer one place, we update the value, and we know that okay, that part is sorted, and then we continue to move the first pointer until again we find the different elements at first and second. Right? So how many passes of the array are we doing, and what will be the time complexity of the approach?
The time complexity would be O of n.
Okay, so we are doing two passes, right? So the first pointer is passing the array once, second pointer is passing the array once. So we are making two passes, so which means this will remain order of n, order of 2n rather. Right? Space wise, we are not using any extra space. So the other more complex solution would have been to keep a map and keep the counts, or keep the unique values, or keep a set and find the unique values and then replace it in the array. But that is obviously a much more, we would be using space for that. So here in this case we are not using any extra space, so we are just using two pointers, so constant space, right? So this is a two pointer solution to this problem that we can come up with. Okay, so this is a good two pointer approach that we can see. Okay. So any questions on this approach? So everyone gets it? Any questions? Let's discuss for 2 minutes if there are any doubts, queries. The only thing that you need to handle in this problem, apart from the algorithm, is that checking the bounds correctly. So sometimes what might happen, that first is going out of bounds or second is going out of bounds, right? The two pointers should be within the bounds of the array, because we are moving the elements. So you should be able to verify those. Okay, so I'm not writing code for this problem. Okay, so let's discuss another problem. So let's discuss a second problem now. So now say we have so this is a completely different problem again. Okay, so we have a set of boundaries associated to us. So say we have a numbered line, and this is, or let's call them 0, 1, 2, like this. These are just the indices of the array. Okay, I'll explain the input. So say at each position of the numbered line, we have some certain walls. Okay, walls with certain heights. So this is a wall of say height 1. This is, so we'll write them also. This is the wall with say height 8. So this will be a taller wall, right? Then we have a wall with say height 5. Then we have, so this is 5. Then we have something like say 3, 5, 4, 8, 3, 7, 2 kind of thing. Okay, so this is 2, this is 7, this is 3, then this is 8, right? What else is there? So we have 4, we have 5, and we have 3. It has to be a bit lesser than 4, so we have 3. So these are nothing but walls, not walls, these are just container sizes, you can assume. Okay, these are, yeah, this can be probable container walls. Okay, so the array basically gives you, so you are, the input is now an array, so you are given heights of container walls where ARR I basically tells height of the wall at position I or at index I, whatever you want to consider. Okay, what you have to figure out, you have to figure out, so this is given to you, so figure out the maximum area of the container or maximum amount of water that can be stored in the container if you are allowed to choose only uh, if you are allowed to choose only two walls. So there are many walls, there are many possible walls, right? You are allowed to choose only 2 walls such that the amount of water is maximum between them. So you have to figure out the maximum amount of water possible. Okay, so in this case, say in this case, if you think if you chose these two, 0 and 1, the maximum amount of water would have been this much only, right? So this would answer would have been 1. If you had chosen these two, then the maximum amount of water would have been height 1 and width 2, so 2, right? But you have to choose the two which have the maximum water stored. So ideally the answer should be these two, where the maximum area will be 7 width and 7 height, so 49. If you argue that these two can be possible answer, these two won't be the answer because both are 8, but the width is 1, 2, 3, 4, 5. So this is 8 into 5, that is 40, which is less than 49. Okay, so the maximum possible answer will be 49 in this case. Okay, so how will you solve the problem? So you are given probable container walls, right? Which 2 walls will you choose so that the water between them is maximum? This is the problem. So think about it a bit, then we'll discuss. So everyone got the question first of all. So this is not a very easy intuitive question, so that's why any questions regarding the question itself. You can ignore the thickness of the walls. Okay, so the walls don't have thickness. They're just partitions, they're there to stop the water. So ideally for this question, you have to just find the maximum amount of water. Okay, so you have to return an integer. But a variety of this question can be you have to return the indices also, which make, or you have to return the indices like a pair, which makes the maximum amount. So for this question, you can assume that you have to do the format that is just return an integer. think about it a bit, not a very easy problem to solve. So everyone got the question, what we are trying to figure out and what the input signifies? Yeah. Okay, so we have one approach. Okay, again we will run. Yeah. So do you want to explain the approach, how you are thinking of a two-pointer solution? It seems a bit far-fetched. How will you code it up like the previous problem?
Sir, I was thinking about using one at the beginning and one at the end. And calculating the maximum area that way. But in this case, we would be missing out some of the pairs, so that is not correct.
Right. So what can we do to solve the problem? Anyone, any other? Or if you want to think of something similar, like have two pointers at the one at the beginning and one at the end, but then what? You can calculate the area between the first and the last, but then what do we do? Or how do we move the pointers?
So like I was thinking, if while the the pointer at the end is greater than the pointer at the first index, why this condition is true, we could have a accumulator variable called max area.
Okay. Then how do we update the pointers? So can anyone tell? Okay, I think there is another message. Yeah, Mirza has some message updating max. Yeah, you have to update the max, but how do you move the pointers? That is essentially the question now, right? So can you think of what is the bottleneck for the area? Like what is determining the area between the two pointers? Let's take this approach itself. We are starting with two pointers, one from the beginning, one from the end. What is the bottleneck that determines the area between the two pointers? What is the area first of all? The area or the amount of water that you can store?
The area is the minimum wall height among the two elements into the difference of
Right?
distance between them.
Okay, so area is nothing but distance, that means last minus first, right?
Into
This is the
minimum of
distance into minimum of right. Everyone agrees to this. So this has to be the area, because if you have a tank like this, then obviously you can fill up water only till this point, not till this point, right? Because then this water will overflow on this side, right? So the minimum of the two heights and the width, this has to be the area. Okay, so if that is the case, then which of the pointers will I be updating, or how will I be updating the left and the right pointers?
the pointer where the height is smaller.
Why and why, obviously the next question. So say in this case 1 and 2 are there as the values, right? So you are saying height is smaller, that is 1, so you want to move the first pointer, then not the last pointer. Why will that be the case?
Because if the height of the wall is greater, the chances of having the maximum area would be greater.
Okay, so you are saying that, okay, I'll just explain it a bit more. So you know that the moment you move the pointers, you know that the width will shrink, right? The width has to shrink, any one of the pointers, even if you move, because this is the maximum width you get. So now the game is only with the heights. Sorry. So now the game is only for the heights. If there is a smaller height, the smaller height becomes the bottleneck, right? Because the next element, whatever it is, the smaller, like even if this element is 100, it can only store, height can only be 1 between this and 1 and 100, right? Height of the rectangle will be only 1, or area of water will be determined by the mean of the two, right? So you will always try to move the minimum one, because you want to see a higher minimum, you want to see a higher value there. Okay, so everyone gets the point. So instead of 7, if we had 100 here, the area between 1 and 100 would still have been this width into 1, right? Because 1 into last minus first, that is say 8. 4, 5, 6, 7, 8, 8 or 7, whatever it is, right? Even if it was 100, so it doesn't matter if we keep 1. But the moment if we move 1 to 8, instead of moving the last pointer, then the area can become now higher because the width has reduced by 1, but the minimum has now increased, right? So the length has now increased. So 2 into 7 or 2 into 8, whatever it is. So the area is now higher. Okay. You don't move both the pointers. So why will we not move both the pointers? Anyone? Why can we not move both the pointers?
Because we will miss out some of the possible pair which could give the maximum area.
Correct. So we have to keep one rooted because we want to see all the possible combinations from first and last. The moment we move both, then we are ensuring that none of the, because of one small value, we are ignoring the other one also, the other wall of the container also, which could have been a possible answer, right? So we have to move either one. So to concretize the algorithm, what do? We keep one pointer at the beginning. We keep one pointer at the end. Right? And what do we do here? So what will be my while condition?
Either last is greater than first.
Okay. So while first is not equal to last, because the moment first becomes equal to last, the width becomes 0. Right? So you don't need to worry about that. So your max anyway is 0 initially. Right? So you calculate the max. The max is nothing but max of whatever the max till now you have and the current area. Right? And the current area you can directly get from this formula. I'm not writing it again. Okay. Then what you do here? The same logic that we discussed. So if the left hand side is greater than the higher than the right hand side, which one will we move? So if ARR first is greater than last, which one should we move?
The last.
The last one. We should move the last one. Else, if the reverse is the case, so if ARR last is greater than first, obviously we move the first one, right? Else, if both are equal, what we can do? So can we handle, if say both are equal, that means you have say 3 here and 3 here, and then you have many other values here. You have the 2 pointers here, say both are equal. So if you move this one, this pointer, both the bottlenecks are same, right? 3 will be the bottleneck. So you can either, so 3 into this area, right? If you move the left pointer, then it will be again 3 into a lower area, a lower width. Sorry, 3 into, earlier it was 3 into this bigger width. If you move one pointer, it will be 3 into the lower width, lesser width. So it has to give a lesser answer. It has to be, right? And if you had moved from this side, still you would have got 3 into a lesser width at max. If this value was even lower, say if this value was 2, then you would have got 2 into a lesser width. So it would have been even less, right? So if both are equal, then either you can move either one. So you can handle the case as an equality, like you can use equal to here or equal to here. Either is fine. Or the best way to handle it is move both. because I don't want to make 3 as a bottleneck anymore. So I move both. Right? So I move both. Okay. So with this, we should be able to get the max at any point of time at the last point, and finally we'll be returning the max. Okay. What would have been the brute force approach, anyone? What would be the brute force approach of solving this problem? Correct. So brute force approach would have been 2 loops, having nested loops to solve it, right? Just going from I 0 to end, j I plus 1 to end, and figure out all possible combinations of I and j such that I is less than j. So that would have been an order n square solution. So with this approach, it's now a order n linear complexity solution. So we are updating the max here itself, right? So there is a question that where is the max getting updated? So we are updating the here max here itself. So max equal to math dot max of max and area. That can obviously be done in 2 steps. So you find the area and then you check if area is greater than max, max equal to area, something like that. You could also have to return. So the question might be, you have to return the pair of indices or the indexes which would make the container. In that case, whenever max get updated, so you make a check like this. If area is greater than max, then you basically change the pair. So res 0 equal to left, res 1 equal to right, kind of thing. So res 0 equal to first and res 1 equal to last. If you had to return a pair, right? If the question was you have to return a pair of indices, where the answer lies. So you could have just done this, and obviously you would have to update the max anyway. So the max will be equal to area. So that can be a follow-up question, can be a bit different question that you need to return, but the approach obviously will be the same. Right, so here we are not using a brute force order n approach. So now we are looking at a order n square approach. Any questions here in this problem? Yeah, go ahead.
We are like in the equality case, if we are moving both the pointers, then we might miss out some of the possible pairs.
Okay, so let's try to
Like
check for that. Let's try to prove that, yeah, that either whether we are missing out or not. So what can be the combination? So we can have 3. Let's see, we have 3s. Okay, so let's say we have a higher number here, or say we have a lower number here and a higher number of 3 to this side. Now say both are 3s. First is pointing to 3, last is pointing to 3. So the moment I move, say I have three options, right? I have three options. One is move first, one is move last, one is move both, right? So let's take the first option, that is move first. So if I move first, what will be the width has reduced by 1, right? Width has to reduce by 1. What can be the height? What can be the height of the new thing, the new rectangle, if the next element from first is lesser than 3? Then the height will also be less, right? So it will be min of the next element and 3, right? So if it was say 5, so in this case it will be 1, the bottleneck height, right?
Yes.
In this case it will be 1. But in the other case, and that's why I kept the array like this, say if I had moved second or moved last, then again width had reduced by 1, but the height would have still been min of next and 3, and here next is a greater number, say 7, so the height would have been 3, right? So height can either be 3 or lesser than 3. It cannot be greater than 3 because one side of it is bottlenecked by 3, right? Say if this was 7, then this side would have been bottlenecked by 3. So your height would remain 3 and your width would reduce. So your answer would have reduced, right? Your answer has to reduce, right? Your area, new area will be less than the max. If this side was say 1 itself and not 7, right? Then if you consider this new area, then also this will now be the bottleneck. So the bottleneck will be 3 or lower. It cannot be a higher value, right? Because one side of the two things, the two pillars, the 2 pointers has been bottlenecked by 3, right? So the width can be either 3 or less, right? So if it is 3 or less, then the max area that you had found initially would have been 3 into last minus first initially. The new area, let's call it area new, would be some value which is like upper capped at 3. So area will be less equal 3 into last minus first minus 1, right? Now because the width has been reduced, and why I am putting less equal, because I have proved that the bottleneck will be 3. The highest amount of water, the height part has to be bottlenecked by 3, right? So you know that the area new will be this, and obviously you can see that this will always be less than max, right?
Yes, sir.
So area new will always be less than max, okay? And not less than equal, rather it will always be less than max, because there is a minus 1 also, so it has to be less than max. So because it is less than max, so you know that the pairs 1 3 or the pairs 3 7 will never give you a better result. The pairs 1 3 or 3 7 will never give you a better result. So you have considered both the cases. So there are no cases that can miss anymore. So now we move both the pointers. From an optimization perspective, it's not much, but still you are improving on the number of operations that you do. Right? This is the mathematical logic behind that. Okay. Cool. So let's go to the next problem. The next problem is pretty simple. So, and this we will spend very little time on this. So say now you have a sorted array. Okay. So you are given two things. One is a sorted array, and you are given a target value. So you have to figure out two elements such that the two elements add up to the target. Okay. So you have this, and say your target is given as 10. So you have to figure out two numbers that add up to the target. So you'll be returning a pair. A comma B such that A plus B equal to target. And if there are multiple possible combinations, you return only one, either one. Okay. So how do you solve it? This should be a very, very simple problem to solve now. Like, how do you solve it optimally? So this problem is seemingly much simpler, right? So you have two pointers at both the sides, and we just check if, because it's a sorted array, we don't need to worry about anything else. So we just we have the first and the last, or left, right, whatever you want to call them, and we just check their sum. So if their sum is less than the target, then you know that the smaller element has to be ignored, right? Because if you ignore the larger element, then you can never reach the target, because this element has to be smaller than 8. So you move the smaller element to the right. So you move this towards the right, and then you again compare. So in this case, you are getting the answer 2 plus 8 is equal to 10. So you are done. So you return 2, 8. A variety can be that you have to return true false kind of thing also, right? That also can be done. Okay. If the question was you have to return all possible values, if you have to return all possible pairs, how would you solve it? Only pairs. So now the question becomes a bit different. So you have to return an array of arrays or a list of lists. Okay. Return a list of pairs that add up to target. So now what do you do? Or let's call it list of unique pairs. So list of unique pairs that add up to target. So for this example, the answer would be 2, 8, and then 3, 7, and then 5, 5. Right? So now this is a twist in the tail. So this answer should be 2, 8. So how do you solve the problem now?
Sir, using the just the previous method, but when we have encountered a pair, we would increment the first pointer.
If you
Like store
increment
that
the, okay, So you are saying you will increment the first pointer.
Yes.
So if I have the array like this, so what will be the answer here by your logic?
8 2.
Then only this?
Yes.
Your answer won't be in only this, because the moment you are moving the moment you find 10, you are moving the first pointer. So this comes here, and then you again see that it is adding up to 10. So your answer will be actually this, which is wrong, because you have to return the unique pairs, right? So there is a minor case that you need to handle. So you will not be returning unique pairs by your solution. So how do you solve that part?
Sir, we could check if the pair already exists in the list.
Very difficult to check. That makes the algorithm order n square again, because now you have to go through the result array, however big it might be, and check for that pair, right? And checking for a pair is more difficult than checking for an integer, because for an integer you can put it in a set and you are done, but checking for a pair you cannot put it in a set.
So we just have to increment the first and decrement the last.
Okay. So exactly. So because you know that if a plus b equal to t, and you know that you have found two elements already, a and b, then at later point of time, if a is part of an answer, then b has to be a part of an answer, right? A cannot be, so it cannot be that a plus c equal to t where b not equal to c. It is not possible, right? So if a is a part of the answer, b has to be part of the answer. So this is not possible. Right, and that's why if you find an answer, you move both the pointers, because you now know that 2 and 8 they have already been solved for. What will be the issue here? Anyone? What will be the answer in this case? If you move both the pointers, what will be the answer here?
2 8 and same again 2 8.
Right, so again the answer is not correct. So this is not solving the problem completely, that moving the pointer, the first pointer by one place, last pointer by one place, it is not solving the issue completely. So now what we can do, or again what we need to take care of?
Find a different element.
Correct. So we have to find a different element on both the sides, right? We have to find a different element on both the sides. So the moment we have found one value, we move both the pointers till we find a new value. So the moment we have found 2 and 8, so we move that the first pointer till the value is not 2. Similarly, we move the last pointer till the value is not 8, right? And the moment we don't find them equal, then again we start the initial work, right? So in this case, say there was another 2, there was another 7 here. So the moment we found first 2 and 8, we move until we find a 3 on the left. So we find a 3 here, so we ignore this completely, and we find a 7 here, right? Then we found 3 7, done. So the left pointer moves till we find a new element, the right pointer moves till we find a new element, so every other thing is ignored. Now we had 4 and 5, they don't match, so only the left pointer moves. 5 and 5 they match, output it, and then again left pointer moves till we find a new element, that is 7. But at that point of time, the next iteration, the left is greater than the right, so they have crossed and we don't process anymore, we are done. right? So these can be small nuances that can be there while you are solving a problem, and these actually give like test case failed, corner case handling, corner cases that fail, right? So these are things that you need to be wary about, need to be aware about, need to think of while you are solving a problem. Okay, on the face of it, very simple problem. But the moment small complexities creep in, it becomes very difficult to solve. Okay, so any other questions? All right, so let's look at one last problem for the day. So we have again a very similar problem to the second question, but obviously a bit more, not exactly the same. So now we are looking at bricks that are placed across the number line, and each brick has width 1. Okay, each brick has width 1. So the height is given to you in the form of an array. Okay, the heights of the bricks are given to you, but the width of the bricks are 1 only, right? So you have like this, say this is 1, then you have say this is say 2, this is 1, this is 3, right? This is again say I'm not drawing it to scale, that's where the problem is. This is say 2, this is again 2, this is 0, and this is say 5. Okay, so say this is the problem, this is the input. So you are given the heights of the bricks at each index, right? Now say you are building a rainwater harvesting system, which means whenever there is some rain, you will be harvesting it between the bricks. Okay, so where will rainwater get harvested? So the rainwater will come here, then the rainwater will come here. Right? So this is where the rainwater will be there. So you have to figure out so figure out the maximum amount of water that you can trap. Okay, so you have to figure out the maximum amount of water you can trap, given that each pillar the width is 1, so these widths are all 1. Okay, these heights are given to you and the widths are all 1. So now how will you solve the problem? So your input is again an array, your output is a integer. Very similar to the second problem. Obviously the logic and the problem is different, but the input and output are similar. In the second problem, you had to choose only 2 pillars such that you can make the area maximum. Now you don't have to choose anything. You have to find the total area. You have to find the total amount of water that will be trapped. Okay, so in this case, the answer would be, how much will the answer be? This area is 1 into 1. Then this area is, this is 2, this is 3. So this height is 1. So this area is 1 into 2. That is 2. And this area is 3 into 1. So here answer is 6. Right? Because this height is 3. So this is 3 into 1. This height is 1. This width is 2. So this is 1 into 2. And this is 1 into 1. Okay, so the answer is 6. So how do you solve the problem? Interesting problem, completely different from the previous one, though the inputs are similar. So how do we solve it? So this is not an easy problem by any means. So if you can also think of a hunch, like if you can start thinking, we can discuss. It doesn't, you don't have to come up with the complete solution. Take your time. Anyone with an initial hunch to start solving the problem?
Sir,
Go ahead, yeah.
we could start with 2 pointers pointing to the first of the array,
Okay.
then move one of the pointers until we find a brick wall which is greater than the height of the first wall.
Okay.
Now that we know the water is to be stored among this wall, we could use a formula to calculate area.
Okay.
then the first pointer would come to the, like the pointer at the beginning would come to the pointer, the first pointer, then the first pointer moves again.
Okay.
So that is until they both reach the end.
Okay. So if you have something like this, then the solution might not hold true. Right? So if you start from here, and this first pointer basically reaches here till they are equal or whatever, greater. Right? So this is one pointer and this is one pointer. First of all, how do you find the area? If you try to find the area, then you will be moving all the elements over all the elements again till here. Right? Over individual elements and finding the area.
Yes, sir. For area, we could first use the formula like the minimum of the two walls.
Yeah, minimum of the two walls, but then the height will not be the minimum of the two walls, first and second, right?
Yes.
The area will be this part now.
Yes, that's what I was saying. The first thing when we, like in the first case, when we reach find 2 and 3, the formula to calculate would be 2 into like the minimum element into two into the position of 3 minus 2 minus 1. Then move the second pointer and subtract the height of the elements in between.
Okay, but then it will become much more complex, right? Now finding out the area has become much more complex. The thought process is correct, but how we can simplify it a bit. So I'll simplify the problem a bit. Okay, simplify meaning I'll reduce the array size a bit. So say if the input was only 213, right? If the array size was only 213, it will look like something like this. This is 2, this is 1, and this is 3, right? So what would have been the answer in this case? The
1.
answer would have been this much, 1, right? Answer would have been 1. Perfect. So how we figure it out? We start from 2, and we see that we can only fill up, like we are beginning at 2, right? Because we have 2 at the beginning, we can only fill up to 2 blocks of water per point, right? So when we know that we can only do it at the point after 2, we cannot fill anything before 2, there is nothing else. So we can do it at 1, but at 3 we still know we can fill up to 2, so we cannot fill any water here on top of it, right? So ignore that. So we see per pillar what is the amount of water we can store. So here after on top of 2 we cannot fill anything, so this is 0. For the second case we can fill 1 unit, right? We can fill 1 unit here, so 1 into 1, and for here we cannot fill anything because this is greater than 2, so your answer is 1. Okay. Now say I increase the array size a bit, I increase the complexity a bit. Say I now have 2, 1, 3, 1, 4 kind of thing. Okay, so how does it look like if I try to draw to scale? This is 2, this is 1, this is 3, this is again 1, and this is 4. Right, so 2, 1, 3, 1, 4. Now how much water will be stored? So till 213 we all know how we can solve the problem. So till 213 it is known to us, right? So this much we know the answer 1. Now the moment I find a higher point, sorry. So the moment I know a higher point, I know that I can fill up to 3 on the right hand side of that, right? So this point I can fill up to 3, but if the right hand side was 2, if instead of 4 this was say 2, if it was only till here, I could have only filled it till 2, not till 3, right? So this gives us an idea that we have to have 2 pointers at 2 ends, because at any point of time we have to look at the 2 possible directions. Okay, we have 2 possible directions. So we have to start the algorithm from 2 sides. So we have to start from here and we have to start from here, and we have to check whatever is the smaller value. Okay, so let's write the algorithm first. Let's try to write the logic first, not the algorithm. So let's try to write the logic here itself in red. So obviously the corner case will be while left is less than right or first is less than last kind of thing, right? And we will be checking if the height left is less than error right. So what does this mean? So that this means that on the right hand side there is a higher value is available. It is guaranteed. You are guaranteed to have some higher value on the right hand side, right? You are guaranteed to have a higher value on the right hand side. So I'll just check in the left if this is the highest left or not. So I'll check if array of left is the highest left till that we have encountered or not. Say I call it max left. So if this is the highest left, then I obviously update it. So I'll update max left. That means this is the biggest, this is the highest one I have encountered from the left hand side, right? If this is not the biggest one from the left hand side, then what I know that there is some value on the left which is bigger than that, obviously, right? Because max left, this is not max left. So there is something on the left which is max, and I already know that on the right there has to be something which is greater than this. So the amount of area I can add, so otherwise I'll add water on top of that. So what I'll do is the total water variable, whatever I have, I'll do plus equal to max left minus this current height, and width will only be 1. Width will only be 1 because I'm going width by width. Okay, so what I did is I find what is the max from here. So in this case I know that at 1 I know the max from here is 2, and say on the right hand side I had 4. So I know that there has to be some higher value here, more than 2. It can be this 3, it can be this 4, I don't care. I know that this part will be filled only till this extent. Till how much extent? Till the value of max that is there, right? If the max would have been, if the max was say 3, somewhere here you had say 3 max left, right? How much value, how much amount of water would you fill here? You would fill this much amount. Why? Because you know that on the right hand side there is something greater than 3 somewhere. It can be here, it can be here, anywhere, right? But this amount will be filled till 3 that you are guaranteed to have. Okay, same thing you will do on the right hand side. Same thing we'll do on the right hand side. So we'll do an else, and we'll mimic the same thing on the right. Okay, so if AR left less than right we have done. So we will do the other part is right is greater than left or equal anything, right? So we will check if height right or ARR right is basically greater equal the max right. So if something is greater than the max right, so we are just mirroring the condition, right? If it is greater than the max right, then max right becomes this. We are not adding anything to the array. Why? You got that point, right? See, on the right hand side you had something like this. Okay, so for this, would you add any water here at this point? Because say this is right is initially 0, so this is your max at this point of time 1. Would you add any water? No, right? Because the water will overflow. So you just say max right is 1, then you get max right equal to 2. Will you add any water here? No, because the water will overflow. Then max right is 3. Will you add any water here on top of it? No, right? Because the water will overflow. Then you get something less. Say you get 1 again. You will add water here because this is less than max, right? So you will add water. So in the else part, you will say that total water will be plus equal to whatever the max height is on the right minus the current height. Same thing that we did in the left, we will do in the right part, right? And when we work on the left hand side, we increment left pointer because it's a 2-pointer solution. We increment left pointer. Then we modify on the right hand side, we reduce the right pointer. Okay, at the end we return the total water. So instead of having just 2 pointers, we are now we are maintaining the max on the left and the right hand side and then building the solution elegantly. Okay. What Rudnan mentioned, we can do that, the approach, but calculating the area of water will be very tough, right? Because at each point we have to see what is the width, what is the height, and can try to figure it out. Now what I am doing is I am intuitively saying that whatever the max left is there, if left is less than right, then I know that the upper bound will be max left for that particular brick, for that particular index. So I'm just adding that difference of heights, right? I'm going brick by brick. So I'm doing an order n solution and solving the problem. Okay. So this is a very interesting problem. This is this looks very simple, but this is actually a hard problem to solve because it's very difficult to do it in order in time and space, order one space and order in time. So it's actually a hard problem to solve. So try it out. I think it is in LeetCode. If you search it, you will get it. We'll do that for you. Not sure if you can see my screen. If you can, is my screen shared? Yeah, okay, my screen is shared, right? Yeah. So if you see in LeetCode, I think it is called trapping water, yeah, trapping rainwater or something like that. Yeah, this problem. So it's a hard problem to solve, and this is how you can solve it ideally. Okay, so you can actually, I'm pinging the link if you want to practice, if you want to see whether all the corner cases are getting handled or not. So try to apply whatever you have learned and try to code it up. Okay. The other problem that we looked at today, the second one, that is called container with most water or something like that. Yeah, container with most water. So again, this is a LeetCode problem. This is an easy problem to solve. It's medium here, but this is a simple problem to solve. Like you to choose 2 points and 2 indexes and find the height. So this is the link to this problem. What else did we solve today? We solved the sorted thing. So that is, I think, do some It is not 2 sum, that is 2 sum 2, I think. Yeah. This is the third problem that we solved. This doesn't handle the complexity that there can be more than one solution. So here there will be exactly one solution. Okay. So this is one problem we solved, and I think these are the 3 things we solved, right? We solved one more thing in the beginning. Okay, this is pushing elements. This I don't remember if it is there in lead code or not, but a similar problem will be there somewhere. Yeah, remove duplicates from sorted array, something like this. Yeah, so the thing, I'm not sure about the padding part. So if it is padded or not, I think this is not padded to zeros at the end, but we modified that problem a bit. But similar problem, right? So I'm putting all the 4 links in the chat. If you are copying it, do it fast. So you can try to solve these problems. So you can go for we'll be solving similar more different problems in 2-pointer approaches in future. Not in the next class, but in future we'll again take it up. We'll take up different genre of problems in the 2-pointer approach ambit. Okay. And yeah, so this is more or less it for today. So I'm stopping the screen sharing. I hope you have copied the 4 things from the message. So we'll wrap. If there are no other questions, so any questions, one last call. Cool. So no questions, we'll wrap then. Okay, so prepare well. Let's meet next weekend. I think it's the Christmas weekend, but we'll have classes. We will be looking at a bit more in terms of patterns. Today we looked at 2-pointer approach, but the problems could have been solved in different ways also. In the next class, we'll take up a new pattern, and then we'll try to solve questions in that genre. Yeah, thank you, and yeah, have a good week. Bye bye.